So welcome back. You can see I have already pre-written a theorem on the blackboard. Please have a look at it. Please have a look at it. I mean, it looks kind of extremely long, but you will see that once we start proving it, it is not that difficult to do once you understand all the concepts geometrically. Okay? So, what it is, as before, we are considering PQR as C1 functions in a domain omega tilde in space, that is R3, and it contains the point x0, y0, z0. And the very next thing you are going to see, is this big condition. So, like say this theorem, I mean in the top book, it has been given like maybe 2-3 lines, and all the previous concepts they have defined earlier. So what I'm trying to do, I'm trying to rope in all the information inside this statement itself, so that it is easier for you to understand it. Okay. So then what it says that then in a neighborhood U of the point x0, y0, of course, what we are doing, this point we are considering the xy plane. So, and of course, U is also going to be a, small neighborhood in xy plane. So then there is a unique solution of this given equation, satisfying this initial condition, this. And you know that this initial condition is nothing but a curved line in what? XY plane, right? And what does it do? Corresponding to that curve in XY plane, you have a curve in XYZ space, right? And basically, what we are trying to do, we are seeking a solution of this equation, which is nothing but an expression of the form z equal to f of xy. So that means we are seeking a surface, right? We are seeking a surface in such a way that the initial curve corresponding to this initial condition is going to lie on that solution surface. Is it okay with everybody? That's what we are trying to do. Is it okay?
Yes.
So basically, what is happening here, I'm telling you again, let me repeat it. I have been given a curve, say C, in some domain omega in xy plane, right? And then we have parameterized that curve C in xy plane, right? Through some variable say t belonging to some interval I, okay? So then what we have done, we have defined another function of the variable t along that curve in such a way that corresponding to all the curves lying, corresponding to all the points lying on the curve in xy plane, I can get a curve, say C tilde in xyz space, right? And then what we are trying to do, we are seeking a solution of this differential equation, which is nothing but a surface in such a way that that initial curve C tilde is going to lie on that solution surface. Okay, and for that we have been given a condition. So this is the condition that has been given at a point x0, y0, z0, which lies on that particular curve. Okay, curve C tilde. Okay, so what we are going to do, if this condition is satisfied, we are going to show that a unique solution surface exists in the neighborhood of x0, y0, z0. And as I told you in my previous class, this condition is a heck of a condition, and it is a killer condition. You will see why I have been using the word killer all the time. Okay, fine. So Let me just again keep this condition as it is so that you can have a look at that. You can have a look at that. Okay. Okay. So what I'm going to do, firstly, let me try to give you a pictorial description. Let me try to give you a pictorial description of the initial condition, and let me like try to show you the curve C tilde as well. Okay, fine. See, my condition is something like this. This is X, this is Y, okay, this is Z. Then suppose I have a curve C here, I have a curve C, okay, and then suppose this is my point x naught y naught, okay, and suppose this is the small neighborhood of x naught y naught, and I'm calling this as u. This small neighborhood has been called as u, okay. So then again this curve I can parameterize like something like this. RT equal to simply x naught t, y naught t. Okay? Where of course t lies in some interval I. Is it visible? Okay, it is visible. Okay, fine. So now corresponding to this curve C, this curve C in xy plane. Now, if we define a function z naught t over the same interval, so that means for all the points lying on this curve, right, I can find a third coordinate for those points x, y lying on this curve, right? So for each of these points, I can get a point on the 3D space, right? And that is going to generate, say, some curve like this. So basically, this is my curve C tilde, okay? And then this is going to be my point x naught, y naught, z naught. Is it okay with everybody? Is it okay with everybody?
Yes.
Right? Okay. So now I am going to do more work there. So now let me just define the vector v as pqr. Let me define this vector v as pqr. Okay. So now, yes. What is happening here? Uh, of course, and I'm assuming that this vector is non-vanishing. Okay, so at least p, q, or r, they are non-zero. Okay, so now let us concentrate on this curve c tilde. Okay, so what I'm going to do, so maybe say this curve c tilde, I can parameterize by this, right? The way it has been defined. Is it okay? Is it okay with everybody? Fine?
Yes.
Right? And that means a tangent to this curve, it will be given by r prime t, and simply this is going to be like, say, dx naught dt. Let me simply write it like this, okay, and dy naught dt and dz naught dt. So far so good, right? Is it okay with everybody? Fine. So now let us see what is happening out here. what I'm going to do, I'm going to claim that at this point x naught, y naught, z naught, x naught, y naught, z naught, your this vector v is not a tangent. This vector v is not a tangent. Okay. Can anybody give me some direction why it is not a tangent? Yes? Any idea that is creeping up? In fact, Hall also, I mean, in his book, he said that it's not a tangent, but he's asking you guys the question. Why? So,
Sir, can you please repeat this question once more?
okay, see, the question is, say I have defined the vector field V as this, PQR, okay, fine. And then, like say I have this initial curve in xy plane, and corresponding to this initial curve, I have this initial curve in xyz plane, okay. So now I am telling you that, and of course, this curve C tilde, it has been parameterized through this x naught t, y naught t, z naught t, fine. And now I am telling you that this vector v, is not a tangent, at the point x naught, y naught, z naught under the prescribed condition. Can you tell me why? Okay, once I do it, then everybody is going to heave a sigh because you will then tell me that, oh my god, it was so easy. Okay, fine. So what I'm going to do, at the point x naught, y naught, z naught, what I'm going to do, I'm going to compute this. Okay, right? I'm going to take the cross product of the tangent at the point x naught, y naught, z naught and the vector v at that point. So then what it is going to be? It is going to be what? I, j, k, then p, q, r, then dx naught, right? So far so good. Is it okay? Isn't it? Right? And of course, at the point your x naught, y naught, z naught, and let us assume that x naught, y naught, z naught corresponds to the point t naught belonging to I. T naught belonging to I. Fine? So then from here, what I am going to get? I am going to get some vector where the third component is going to be given by what? This p dx naught, sorry, dy naught dt minus q dx naught dt, isn't it? Of course, this has been taken at the point x naught, y naught, z naught, or t equal to t naught, isn't it? Fine. I have some component here, Is it okay with everybody?
Yes, sir.
Are you getting why I mean v is not a tangent?
Yes, sir.
Why? Yes?
Sir, so this is non-zero.
Exactly. See?
This is not.
Yes. See, this is the giving condition. I told you this condition is a killer. Right? So now is everybody understanding it? Look at the giving condition. This giving condition is nothing but the third component, isn't it? Right? The third component and x naught, y naught, z naught, and of course t corresponding to t naught, right? This is the third component is nothing but the left hand side of the given condition, right? A. Okay. And we have been given that this is not equal to 0, right? This is not equal to 0. So these cross product at the point x naught, y naught, z naught, it cannot be equal to 0, right? So that means these two vectors are not parallel. Is it clear?
Yes, sir.
Right? These two vectors are not parallel. So that means So that means your V is not a tangent. V is not a tangent to the point, a tangent to the curve C tilde at the point x naught, y naught, z naught. Fine. Okay. So far so good. So now, what about so if V is not tangent, so that means what? That means C tilde is not an integral curve of V tilde, isn't it?
Yes. Yes.
Right? It is not an integral curve of V tilde, right? So now, if it is not an integral curve of V tilde, so definitely I know that we have a procedure. Like we already know that if you have an initial curve, which is what? Which is not an integral curve, right? Then what? You can get a unique solution. You can get a unique solution what? xyz of the differential equation given by pux plus qey plus ruj equal to 0, right? Is it okay? Isn't it?
Yes.
Right? On which the curve C tilde is going to lie. We have already done this before, isn't it? We have already done this before, right? So that means I can find an integral surface of this type. I can find an integral surface of this type in such a way that this happens. Right? So far so good, right? Up to this you are fine. Isn't it?
Yes.
Right?
Yes.
See, this V being not a tangent, it is simply to tell you that I am going to have a unique integral surface. That's it. Okay. The other case, I am going to come back to that later on, but let me first finish this. So definitely we have a situation like that. But in the original theorem, see, you know that we are interested in this. We are interested in solution of this, isn't it? We are interested in solution of this. So that solution I am seeking in the form of this, Is it okay? Fine. So if I want a solution in this form, right? I must be able to extract J out of this equation, right? J out of this equation. So, right, there must be what? There must be some implicit way of defining J as a function of x and y. Is it okay? Fine?
Yes.
Right? And I can get that what? I can get that through implicit function theorem. Isn't it? Say uxyz, it is going to define a solution of this equation, right? Implicitly for j, if what? Uz is not equal to 0. Is it clear to everybody?
Yes.
Right? And I am seeking the solution in the neighborhood of x naught, y naught, z naught, isn't it? So, if I can prove that uz is not equal to 0 at the point x naught, y naught, z naught, then I am done. Is it okay? Fine. So that is what we are going to do now. That is what we are going to do now. And don't worry, I'm going to give you a better, graphical presentation of the situation, because because I was just want to hold this condition A for some time, so that is why I didn't draw it maybe clearly. See, now obviously I think you can remember this condition, right? So I am going to remove this. Okay. So next thing I am going to prove is that this is not equal to 0 at the point x naught y naught j naught. Okay, fine. See, yeah. So now, see, this is an integral surface, right? This is an integral surface. Is it okay? This is an integral surface, right? So that means this being an integral surface, it means that at every point of and again integral surface of the vector v, right? At every point of this, including the point x naught, y naught, z naught, what is going to happen? V is going to be a tangent to the surface. Is it okay? Fine. V is going to be tangent to the surface. Is it okay?
Yes, sir.
Right? So that means I mean like if I find out grade u at x naught, y naught, z naught, and then this at v x naught, y naught, z naught, this is 0, right? Isn't it?
Yes, sir.
Right? So that means basically grade u, you already know it. I am just simply repeating it. This is perpendicular to v, of course, at x naught, y naught, z naught. Okay? So let me call it c. Let me call it c. Okay? Fine? And again, see what is happening? What is happening? This is nothing but a tangent, right? This is nothing but a tangent, isn't it? This is nothing but a tangent at x naught, y naught, z naught to the curve C tilde. Fine? Isn't it? Right? And then what is happening? Then what is happening? So that means this tangent vector, it must lie on the tangent plane drawn to the surface this at the point x naught, y naught, z naught. Isn't it? Fine?
Yes, sir.
So that means r prime t naught, again this has to be perpendicular to grade u, because this is nothing but a normal at the point x naught, y naught, z naught to the surface given by this, isn't it? So this is also perpendicular to this, right?
Yes.
Is it okay? Fine. See, now I have been given that r prime t naught and v, right, at the point x naught, y naught, z naught. Oh, they are not parallel. They are not parallel by the given condition, right? But I know that their cross product is a vector which is perpendicular to both r prime t naught and v bar, isn't it?
Yes, sir.
So basically, I'll tell you what is happening here. See, I have a situation like this. Say, suppose this is your r prime t naught. Suppose this is v prime. Sorry, v, and I am considering at the point x0, y0, z0. They are not perpendicular to each other, right? But both are perpendicular to gradient. Is it okay? This looking like a straight line? Okay, maybe. So basically, what is happening? Sorry, this is 90 degree. This is 90 degree. Are you getting my point? This is 90 degree, and this angle is 90 degree. Is it okay?
Yes, sir.
I have this situation, right? So what does it mean? Say this is a vector perpendicular to both r prime t naught and v. So that means the direction of this vector must be along the direction of grade u. Yes?
Yes, sir.
Is everybody fine with this? Okay? So of course at that point x naught, y naught, z naught. Okay? So that means grade u at x naught, y naught, z naught is equal to some non-zero scalar into your disk v and v at x naught, y naught, z naught, of course, right? Okay, fine. So that means here lambda is not equal to 0. Remember. Yes? Is it okay?
Yes, sir. Yes, sir.
What does it tell you? So I have already been given that this is non-zero, right? This is non-zero. So that means uj and x naught, y naught, z naught is not equal to 0. Fine. So that completes the theorem. That completes the proof of the theorem. Is it okay? So now you realize, probably now you have begun to realize why I say that particular condition is a killer. Is it okay? Fine? Right?
Yes, sir.
So that means in order to solve an equation of the form pzx plus qzy equal to r under this prescribed condition. So basically what we have to do, we have to find out what some integral surface for pux uy plus ruz equal to 0. That's it. Is it okay? Fine. Now let me come back to the figure. Please, look carefully. I'm going to make some more comment on that. And again, I request you to write down the proof on your own based on whatever I have taught you in class systematically. Because even in the book also, they haven't described everything in detail. Okay, fine. Let it be here. Something like this. So then this is okay. You know that this is x naught y naught z naught. I'll change it accordingly. So then I kind of have a surface like this. This surface is u xyz equal to 0 or z equal to f of xy, z equal to f of xy, and again such that what? Such that what? This such that z equal to yes. You have to rope in the initial condition. Uh, this may be you can write xy belonging to u. That is the neighborhood of x naught y naught. Okay, fine. So now what is being given? That say suppose this is your capital R prime T naught, okay, and suppose this is like V, and this is grade. This is grade. Is it okay? Fine. So now, this is fine. I mean, if you want to ask me some question, you can ask me. Is it okay? So this point is, I can write it x naught, y naught, z naught, this point. Okay, this curve is C tilde. Okay, fine. It is fine with everybody because I am going to ask you a question now. Yes, the figure you have understood relating to this theorem? Fine. Okay. So now let me ask you a question. Say suppose I take the projection of V on xy plane. Is that going to be a tangent to the curve C on the xy plane at the point x naught y naught? Yes? Is it what it is going to be? You say my question is V a tangent to the curve C at x naught y naught in R2? This is my question. You think about what is going to happen to V if this happens. I have given extra hint.
Sir, I think this will not be a tangent.
Why?
Because if it be a tangent, then the cross product will be zero.
Cross product. No, but cross product will be cross product of V and
Yes.
R prime T naught. Okay.
Yes.
Okay.
Yes.
So you are thinking in that way. That is, yeah, that is fine. But I can give you an even simpler explanation. Okay. See, if you look at the component of small r and capital R, right? The xy component of both of them, they are the same, isn't it? At the point x naught, y naught, z naught. Agree?
Yes.
Isn't it? So obviously here it is going to be your the tangent to the curve C at the point x naught, y naught, it is going to be simply given by simply this dx, right? And this is at t equal to t naught. Fine? Okay. Now, if V has to be a tangent, I mean projection of V has to be a tangent here at this point. So then what must happen? The projection of V, say, let me call it VP, say. So projection of V, this is simply PQ on XY plane. Is it okay with everybody? Right? You are getting my point?
Yes, sir.
So then what must happen? If they are to be parallel, one must be a scalar multiple of the other. Isn't it? One must be the scalar multiple of the other. Agree? Fine? So that means r prime t naught must be equal to lambda into Vp. Right? Isn't it? So that is going to give you dx naught dt by p equal to dy naught dt by q what? This is going to be equal to lambda, isn't it?
Yes.
Yes.
Right? So if this happens, then the given condition is not satisfied, isn't it?
Sir, I also told you the same thing.
No, I understand that. I understand that.
So for
Yeah.
that you will get this condition.
Yeah,
Uniqueness.
because the cross product thing, again, like say if I want to visualize it, I have to visualize it in 3D, right? Okay, so even without that, say even without thinking about the cross product, I can think in this way also, right? Isn't it? And of course, I have a hidden agenda why I am doing this now like that. Okay, because the next theorem, whether I'll be able to reach that or not, that is going to involve that concept. Okay, now everything is clear geometrically. Okay, so under this prescribed condition, the projection of V cannot be a tangent to this curve on xy plane. Okay, fine. So now, and again, say I have been telling you about this initial curve and like say the corresponding curve in space. So whenever you are given a problem, it is not only about solving the problem. Okay, you should try to visualize it geometrically also. So what I mean by that, so whenever you have the initial curve, you should try to plot it in the xy plane and try to find the corresponding curve, initial curve C tilde in xy j space. That is what I mean by that. Okay. So let us try to. So now another thing that I have given you a geometric visualization of this. Let me tell you that in order to solve problems like this, if you are to find an integral surface, if you are to find a solution surface, for this equation corresponding subject to this given condition. So then you simply have to, you simply have to what? Simply have to find what? Integral surface from this relation, right? And because for the unique solution, when the initial curve was what? Not an integral curve, we knew that what we did, we found out two first integrals, right? And then what we did along this curve, okay, or along this curve, what we did, we tried to equate u1, which is nothing but small u1 as a function of t, and u2, which is nothing but small u2 as a function of t. So what we tried to do, we tried to eliminate t from those two expressions, right? And then we constructed an integral surface out of that. Is it okay with everybody? Right? Isn't it? Fine. So now we are going to do that. Let me take an example. So there is a beautiful example which is worked out in the book. I am not going to do that. You please have a look at that. You please have a look at that. I am going to take another example. Okay, fine. So 3.1. So you have to solve this initial value problem. This is y z x minus x z y 2xy z, and you are giving that z equal to t squared on the initial curve, c given by x equal to t, y equal to t, and of course t greater than 0. Yeah, y equal to t. Yes, fine. Okay, so now obviously here what is happening? See, small r_t, this is tt, right? Isn't it? And then capital R_t, this is tt t squared, of course, for t greater than 0. Is it okay with everybody? Fine. Now, firstly, what you have to do? You have to find out p. Let me call it maybe I can y dot minus q x dot. Dot means derivative with respect to time generally. So t, let me think that it is, or okay. If you find it, sorry, dy not dt, d x not dt. So this is going to be what? P was what? P is y, isn't it? Right? P is y, and y is t, and dy dt, definitely both of these are 1, right? Okay, and then q is minus x, so that is minus t, and of course dx not dt, that is also 1. Is it okay with everybody?
Yes.
Right? So this is 2t, and of course t is greater than 0, so this is not equal to 0. So that condition is satisfied. Okay? Fine? So now, I mean, the associated equation is given by this. I think you called it auxiliary equation. So dz 2xyz. So obviously from the first two, I am going to get something like u1 equal to x square plus y square. Is it okay? Fine. From the first two, it is straightforward, right? Isn't it? X dx plus y dy equal to 0 it will be eventually. Is it okay?
Yes, sir.
Fine? So, how to get the second one? Flu is in this xy. Okay, see, I will have then what? This is xy minus xy. So this is minus. So 2xy, isn't it? Fine?
Yes.
So this is equal to dz by what? 2xyz. Okay? So from here, I get something like x square minus y square equal to something like cz, right? Okay? So u2, I can write it as j e to the power minus x square minus y square, right? Yes? Yeah. Is it okay with everybody? Fine?
Yes, sir.
Fine. So then let us find capital U1 and capital U2. So on the curve, say C tilde, your so on C tilde, your U1, this is equal to what? 2t square, right? And U2 equal to simply t square, because x square minus y square, that is 0 on the curve C tilde, right? So it equals 0, 1, simply it is j. So j is t square. Okay, fine. So this implies your u1 equal to 2u2, right? Is it okay? Fine? Yes?
Yes.
Right? So therefore the required integral surface or solution surface is, or required solution also eventually you arrive at, don't worry about it. So u1 was what? So x squared plus y squared uh, equal to 2z e to the power minus x squared by y squared, and this is going to give you z equal to what? Half x squared plus y squared e to the power x squared minus y squared. Okay, fine. This is the required surface. Okay, fine. So now just one thing I. So for this particular problem, can you tell me about the initial curve C on xy plane? Suppose this is positive x-axis, this is positive y-axis. Yes?
Y is equal to x prime.
Y is equal to x. Okay, fine. So it is going to be something like this, right? Is it okay? Of course, because t.
Yes.
Huh? Can you tell me now about the corresponding curve C tilde? Yes?
Z equals to x square z equals to y square.
So that means it is going to be
Intersection.
It is going to be something like this, isn't it? In the shape of a parabola. Yes or no?
Yes, sir, yes.
Right?
Yes, sir.
It is going to be in the shape of a parabola, something like that. Of course, the visualization is not that good, but you should imagine, right? It is going to be in the shape of a parabola like this. Is it okay? Fine. So this is my C, and which is given by x equal to y. Okay, and this one is C tilde. I mean, it is up to you how you perceive it. X equal to y, so z equal to x square also you can write. Okay, or simply in terms of the parameterized expression in terms of a vector, you can also express it. You know how to do it. Is it okay with everybody? Right? So now, one thing. Say, if you look at the solution, so obviously the solution, once you plug in these values along the curve C tilde, it is going to be satisfied, isn't it? Because say here again, this is 0, right? This one is 0 because x equal to t, y equal to t. Is it okay? Fine. And then
Yes.
e to the power 0, 1, and then this is 2t square divided by 2, that is simply t square, right? So it is satisfied there. So that means the curve lies on this surface, isn't it? The curve lies on this surface. Now, if you look at this, you see that this is kind of a parabola, isn't it? This is kind of a parabola, and because of that, because of that term x square minus e to the power x square minus y square. So what is going to happen here? It is going to be a very flat kind of parabola. So if you have some plotting device in MATLAB, you can try it. Okay, you can just check it that it is going to be a very flat kind of parabola. Okay, fine. If you have some plotting device, you please try it at home. Okay, fine. So now what I'm going to do, I am going to just take another example.
Sir, I have a question.
Yeah.
Sir, what are the drawbacks of this Lagrange method?
What are the drawbacks? I mean, instantly, I cannot tell you what are the drawbacks. Like, see, basically what? That those multipliers, it allows you to solve this equation in terms of some exact differential, isn't it? Right?
Yes.
Okay. So, but the thing is that it may not be possible to do that all the time. See, whatever differential equation we are trying to solve, there's some kind of specific example where, like say, they have been formulated in such a way that I can eventually use Lagrange's multiplier and eventually solve them, isn't it? Now, if by multiplying the respective term with some multiplier, you cannot convert or you cannot arrive at some total differential, then it is going to fail. No? That is what it is. And again, remember, like this study, it cannot incorporate all the differential equations. Okay, right? Differential equation of this type definitely.
Which we can integrate. There is so many functions we can count that we cannot integrate.
That is what it is, na? So that is why the numerical methods are. Yeah, so that is why numerical method is going to help you.
Yes, and sir, one other thing, we are writing dx by t equals to dy by q equals to z by r. So what about the analyticity of those?
What about the
analyticity? Means we are writing in this way, but p, q, r may be some function in some domain.
No. Just a minute. Let me tell you. So that's a good question. See, analyticity. See, PQR. What were they? They were class C1 function of XYZ, right? Isn't it?
Yes.
And remember, like say this dx dt, dy dt, dz dt, right? They had come from a curve. They had come from a curve. Remember that. They have come initially. It has come from a curve, and then we had extended it to the whole surface. Based on that curve, we were constructing a surface, right? So we have already defined x, y, z themselves to be a class C1 function, right, over the interval I, isn't it? So then analyticity, it has already been taken care of through that. So without that it is going to fail. Without that it is going to fail. Okay.
But PQR maybe somehow zero. So we are writing this way in the Lagrangian way, this numerator denominator form.
Definitely. I mean, it is going to work only for, yes. It is going to work only for non-vanishing thing. That's it. Yeah. That is one word.
And also, sir, this Lagrangian, I think it is the old method.
That is why, I mean, you guys should appreciate those old mathematicians more, right? Despite having all the facilities now, we haven't been able to devise any new thing. That's where you guys are going to do research and try to find out something new, isn't it? See, despite all the limitations, those great mathematicians, right, in those, I mean, olden days, like in 18th century, 17th century, they have developed such kind of theorems, isn't it? So you guys should appreciate them.
Yes, of course.
So now let me consider this Pxyj. You will see that this has kind of a typical form. XYZ, and this your initial curve is given in this form. I'll give you a geometrical view, and after that I'm going to tell you what is happening here. Say, you may be thinking that, like say, I still haven't come to the term characteristic curves or method of characteristics. Okay, where your syllabus has all these characteristic curve, etc. So probably I'm going to tell you only tomorrow. Then you may be thinking, oh my god, we have missed so many things, characteristic, nothing we have done. No, I have already given you all the ingredients, all these theorems. So then, if you now consider any other book on PDE which deals with first order PDEs, then based on whatever I have taught you, you will be able to do any, I mean, at least those examples or those theorems whatsoever, you will be able to tackle. Tomorrow I am going to tell you about characteristic. So in that context, this equation is very, very important. So now, okay, before going into the mathematics of this example, let me try to go to the geometry. See, x, y, z. Okay, so now can you look at the initial condition? So what is the initial condition? I mean, let me just try to find it out on xy plane, that curve C. Yes? How are you going to parameterize it?
We can take x equals to t.
We can take. Yes, so.
X equals to t. Y equals to t naught.
It is simply y naught. I don't even have to. Because that is constant, right?
And z equals. Yes.
Right? Okay. And RT, T, y naught, some function of x.
Ft.
Right? Isn't it? So, basically, this is what? This is what? Y is y naught. This is, say, suppose this is y naught. So, basically, this is what? This is a straight line parallel to x axis, isn't it? Is everybody getting me? Right?
Yes, sir.
This line is simply y equal to y naught. Fine? This is my initial curve. That means a straight line on xy plane. So, what is happening here? So, basically, what is going to happen? So, based on what is the shape of f of x, so you are going to get something like this, where this is given by f of x. For all x varying along this line, you are going to get something like this. Have you been able to visualize it now? Is it okay? So this is C, this is kind of C tilde. This is kind of C tilde. So this particular situation you are going to get in all, real life phenomena, all real life phenomena. So what they do, generally they take this variable y as the time variable. Okay, fine. So and then they see how the solution is evolving with respect to time. Okay, so now in this particular problem, now if I want to calculate, say dy naught dt minus q dx naught dt, right? So because your y naught equal to 0, this is anyway 0. I don't need to worry about it. Fine. And what is happening here? What is happening here? Q is simply 1, isn't it?
Yes, sir.
Q is simply 1, right? And here x is t along the curve C, right? So that is why dx dt is 1. Is it okay with everybody? Right? Dx naught dt. These are nothing but what? These are nothing but what? X naught t, y naught t, isn't it? These are nothing but x naught t, y naught t. So this is equal to minus 1, not equal to 0. Minus 1, not equal to 0. Is it okay? Fine. So through the given theorem, you'll be always able to find what? An integral surface, isn't it? Right? See, so that means whenever you are given a differential PDE of first order of this form, then there always exists a unique solution in the neighborhood of some point x naught y naught. Is it okay? Fine.
Yes.
So most of the time, what they are going to do, they are going to give you this as 0. They are going to give you y naught as 0. So then, what happens? Because what they do at time t equal to 0, they will be defining something, some initial condition along the x-axis. That's it. Okay, fine. So this is about this one. How much time do I have? Okay, fine. Now, so hopefully in tomorrow's class, I will be able to touch upon shock. Have you heard about shock? You haven't heard about shock? Nobody? Yes? You haven't experienced it? Oh my god, everybody is so silent. This time you haven't experienced. When did you experience it?
Sorry, sir.
When did you guys experience shock?
Shock. Means in real life.
Maybe.
Shock happens in so many areas, like in air flow, you can say in jet plane flow. In the jet plane, we can feel shock or bomb blast.
Okay.
Bomb blast like this.
Has anybody ever experienced an electric shock? No? I know that all you guys, you have experienced shock. You know when? When you were expecting like something like 95% in an exam, and you end up with something like 35%, then it's a shock, right? Isn't it? You disagree? Agree? So basically what is happening? So some function, like you were trying some function, say that function, like say something like it should have been some 95%, but all of a sudden it came down to some 35%. Had it been something like say 94.8, right? I would have accepted that, right? Life would have been smooth, isn't it? So that means shock is going to be what? Associated with some kind of discontinuity. That is what we are going to do in tomorrow's class. But let me tell you, tomorrow I am going to deal with non-uniqueness and non-existence of solutions of, let me call it simply solution, of your first order, your quasi-linear PDEs. Okay, so let me just introduce you to this. Tomorrow I am going to do the theory part. See, all the condition remains the same. All the condition remains the same, except for the fact that when like p x naught y naught z naught, then dy naught dt minus q x naught y naught z naught dx naught dt. So when this becomes 0 at the point x naught y naught z naught, at the point x naught y naught z naught of the initial curve, say c tilde, of the initial curve c tilde. So now the question is, does a unique solution exist, or if at all a solution exists? That is different. If at all a solution exists. So that's what we are going to discuss in tomorrow's class. But maybe I can just simply give you an idea what happens here. So the first part, let me do it today. Under these conditions, what can happen? See, we are seeking solutions of these differential equations. Say q z y equal to r, and of course you know what is p q r. They are C1 functions of x y z in some domain omega tilde in R3, right? So now obviously we will be given an initial curve C, right, on xy plane, right, and then corresponding to that I'm going to have an initial curve C tilde in xyz space, okay, and both of them, I mean, it can be parameterized, right? And if j, say this is the solution of this differential equation, so then what must happen? On the curve C, if I like say if I parameterize this curve C tilde by this, okay, so then what must happen along the curve C, if you want to find out dz naught dt, so this is simply what? Your zx dx naught dt plus zy dy naught dt. Agree? Fine? Isn't it?
Yes.
Right? So then what must happen? What must happen? So now, if this is the condition that has been given, this is the condition that has been given. So then what must happen? From here, you can see that dx naught dt by p equal to dy naught dt by q, isn't it? This I have already done today at some juncture. Is it okay with everybody? Yes? From here, of course, at the point x naught, y naught, z naught. Is it okay? Fine? See, suppose instead of the previous condition, which was this is not equal to 0, I have been giving this to be equal to 0. So then this is going to imply this, isn't it? At x naught, y naught, z naught. Yes? Am I still connected? I think, yeah, so we are connected back, right?
Yes, sir.
Okay. I think there was some connection failure here. Okay, fine. So I don't know, I mean, from where this part we were still connected, right? When we did this part,
Yes, sir.
right? So now, okay, now look at the given condition here. From this condition, I can get this, isn't it? Right? Is it okay?
Yes, sir.
So, of course, at the point x naught, y naught, z naught. So let me call it as mu, where mu is not equal to 0. Mu not equal to 0. Mu not equal to 0. So then, from here, what I can write, and say, suppose I am evaluating this at the point x naught, y naught, z naught itself. Okay? So then, this is going to give me simply pzx plus qzy. Right? Okay? Fine? So, if z has to be a solution of this equation, right? Then from this expression, what I must have, so this is equal to what? Mu r. Again, it is gone. Am I still connected?
Yes, sir.
Okay, okay,
Yes.
okay. So fine, it has to be mu r, isn't it? So what does that mean? What does that mean? So in order for z to be a solution of this equation, what extra condition I'll be needing? I'll be needing that dz naught dt divided by r, this also has to be equal to mu. Is it okay? Fine?
Yes, sir.
So, I am going to show you that if, say, this happens, but this doesn't happen, then I'm not going to get a solution. There won't be any solution. And if that happens, there are going to be infinite number of solutions. Okay, so that's what I'm going to do in tomorrow's class. Okay.